Okay, so good morning, everybody. Welcome to today's seminar. Today we are pleased to have Professor Chung, who is visiting us for 1 week. She is an assistant professor in the School of Electrical Engineering at KAIST. Her research interests include mathematical data science, machine learning, and information theory. She received a bachelor's degree from KAIST and the PhD degree from MIT. From 2014 to 2017, she was a research fellow at the Department of Electrical Engineering and Computer Science at the University of Michigan. So she has received a number of awards, including the KAIST Technology Innovation Award and the Department Teaching Award. So beyond just reading this, Haiwan and I go back a long way. We were graduate students together at MIT. And some of you may know me as someone who dabbles in information theory. And this is in no small part due to Haiwan and I learning information theory together in the fall of 2010. We read the book together with a few other colleagues, and that was how I got into it for many years. Okay, so thanks to her.
Thank you.
So today we're going to talk about data valuation, and please, the floor is yours.
Yeah. Thank you very much for the kind introduction, and thank you for inviting me to this nice, wonderful Singapore University. This is my first time to visit here, and I really enjoyed talking to you guys. So I'm very happy to also give my talk today and hear about your feedback on this work. So today I'll talk about data valuation, and data valuation is really about understanding the value of data in training machine learning algorithms, including the neural networks. So let me start my talk with some motivation of why we consider the value of data. So as we all know, we live in the era of data flood. Massive data sets are really generated every day by human online activities and sensor networks or Internet of Things. And these data sets provide us some new opportunities to understand the phenomena behind the data. And one of the typical type of the data we encounter today is the images. So ImageNet, as we all know, is the very common public data set widely used in training neural networks for computer vision tasks. And ImageNet is really a big data composed of more than 14 million images, including more than 20,000 classes, concepts. And for each concept, there are more than 100 examples. So it's really a huge public data set, image data set, actually generated by Stanford Group with much effort using the crowdsourcing platform to get the correct labels for all these 40 million images. And now the challenge, of course, as an engineer is where to use this kind of big data, and especially how to train a good machine to recognize all the images to have great computer vision ability. And as we all noticed, the big data combined with the massive computing power enabled the recent progress of deep learning technologies, which has great performance in many computer vision tasks. And I just show you one a little bit old example of the deep learning network here today, which is GoogleNet. It was developed 2014, I guess. And GoogleNet is composed of many layers of convolutional filtering plus max pooling. And what we do in training this kind of big network, like composed of 60 million parameters, I guess, is to actually find good weight on this network to make the network tuned to maximize the accuracy on the training set, like to fit all the 40 million images of the ImageNet, for example. So the research was surprising. This kind of machines actually have the ability better than human beings in recognizing, detecting, or classifying images. And many people now understand the power of the neural network with two reasons, basically more data and the faster computers, better computing power. But today I want to address a little bit different view on this kind of stream of works. So my question is, do we need all such big data? So as I said, to collect the ImageNet data, it took a long time, like more than 5 years, and really many people, more than 100 people were in the job to label the data. So actually acquiring good quality data is really a costly job, even in this era of big data. But there are some interesting experiments going on to see whether we actually need such large amount of data. So I just brought one example of such experiment here, presented last year's NeurIPS conference. So what they do was the following. So this kind of experiment is called data pruning experiment. So what they do is, as they increase the fraction of data set pruned, eliminated from the whole data set, they actually see how the test performance, the performance of the trained model changes. So this purple line is the max test accuracy achievable when you use the full data set. And this red line is another reference when you actually randomly prune the data. So yes, you can see the power of the big data by observing this gap between the performance you can achieve with the full data set and the performance you can achieve with the pruned data set. So when you remove half of the data, yes, there is actually a gap. But the surprising result is that when you prune it in some clever sense, meaning you define some valuation scores and prune some useless data, surprisingly, at the beginning, you actually achieve better performance even compared to the case when you use the full data set. And that means in the big data set, there are some harmful examples actually ruin your performance. And another surprising observation is that even when you prune about half of the data set, preserve only half of the examples in the data set, you actually keep the performance near that of the model trained with the full data set. So this kind of observation is made for several public data sets, including ImageNet, Cypher10, Cypher100. So now people kind of understand that actually there exists some redundant and possibly non-important instances, or sometimes harmful instances in the big data set. So as a data scientist and a machine learning engineer, what we try to do is to find such important data sets, the subset of important data sets in the big data only, and then only use that. Since using small data set is always efficient in terms of memory and computation. But the main question here is how to select important data instances. So there should be some scoring algorithm to automatically select good quality data. So this field is called data valuation. And as I explained, the goal is to quantify the value of individual data instances in optimization and generalization of the neural networks. And here, what's important is this individual, the quality of individual data instances, not the whole data set. And there are many applications related to this data valuation problem. So the first application is the data pruning that I just explained, finding a good subset of data with which we can train the machine without the performance degrade compared to the case of using the full data set. And another interesting application is in designing the learning algorithm, the training algorithm. So when we know which sample is important in terms of generalizing your model, you can actually put more weight on the sample by using some importance-based weighted sampling or in the defining your loss function. Or you can design nice curriculum learning algorithm to show important examples more frequently in the beginning or at the last, and so on. So there can be many possible algorithms using this kind of data valuation. And another important application is in terms of noise filtering. So if you know which data is actually harmful in the overall data set, you can simply remove the data in your training process. So there are many applications regarding this data valuation. And there are many previous works on this field, actually from about 5 years ago. And I categorized such method into two big categories, the statistical view and learning view. So let me briefly explain what those views are in quantifying value of data. So first of all, statistical view tries to quantify how the model changes, how the performance of the model changes when certain training instance is removed from your data set. So it's easier for you to see the two examples of such statistical view scores. So the first example is the leave one out method, where you just take out one example from the data set and see how the model changes due to the effect of that remover. So here, an example of this kind of leave one out method is the consistency score. So here, consistency score is defined for example, X is the image and Y is the label of the image. So for a certain instance, and how it is defined is the following. So we measure the expectation of the probability that the model F trained with the data set, but without that instance, still can predict the correct label Y for the instance. So when you do not use the instance in training, what is the probability that still the model can predict the correct label of that data? That is the consistency score. So it means that, so for example, if the data have a low consistency score, that means that the data is actually needed to be memorized in the neural network for the network to have the ability to classify the data correctly. So from that sense, by measuring the consistency score, you can actually identify the data the network should look at during the training, or the data that's kind of redundant, so you can remove without any cost in performance. And another widely used valuation score is the data Shapley, developed in the paper from ICML 19. So here, the data Shapley is defined as the average gap in performances when an instance is removed. And here, the averaging is over any subset of the data in the full data set. So when n is the total number of samples in the data set, you actually pick any subset S. So there are 2 to the n possible subsets in the data set. And you kind of average out the performance gap between the case when you use the data XY in the training and when you don't use the data. And here to measure the performance, you need to have some validation test data set. You need to set your architecture of the neural network and algorithm and so on. So in this kind of data Shapley value calculation, it really requires high computational cost and retraining of the neural networks many times, actually exponentially many times in terms of the size of the data you want to calculate the scores. So more efficient way of calculating value of the data, another stream is learning view. So this learning view basically uses the statistics from training dynamics of your neural network. So training dynamics means the behavior of a model on individual data instances during training. So as an example, a widely used score, one of the widely used score based on the training dynamics is the forgetting score. And what it measures is the number of times during training, the decision of the network on the sample switches from a correct one to incorrect one. So during this capital T time of training epochs, you see how many times the output of the network changes from the correct classification to incorrect classification on the data, XY. So it kind of measures difficulty of learning the sample on the training in the full data set. And another quite simple score is the error L2 norm score, which simply measures some expectation between the network output and the label influence, the gap between the two in L2 norm sense at certain epoch T. So there are many, let me say, empirical simulation research showing the effect of these kinds of scores in terms of data valuation in finding good quality samples. But as you can see, all these data valuation methods, actually, most of that require high computational costs. And here, high computational costs, what I mean is actually training of a model. So for example, in the statistical view, we saw the C-score, consistency score definition and data Shapley. And from the definition, you can see that to measure the performance gap while holding out some instance, you need to actually retrain the model without the data and with the data and so on. And such kind of retraining for data valuation, maybe someone say, it contradicts the motivation of the data valuation sometimes. Because if your motivation of the data valuation is really data pruning, you want to just select the data and efficiently train your model. For data valuation, if it already requires such high computational cost of training, why do you do the data valuation? So I think it kind of contradicts the motivation of the data valuation if it requires too much computation. So that's the question I would like to address here. So how to quantify the value of data without training of a model? That's the first question. And the second question is, all the previous scores that I introduced actually require the label data with the clean labels. But we know in practice, like collecting clean labels is really costly job. And we encounter many big data examples without labels, and we still want to do the data valuation for such data as well. So the next question is how to quantify the value of data without labels. So that's my next question. So here's the outline. I would like to partially answer these two questions in my part 1 and part 2 of the rest of this talk. And if you have any questions, I will be happy to answer if you raise your hand at any time. So then let me move on to part 1, data valuation without training of a model. So this is a joint work with my 2 students, Donghyun Ki and Hoyoung Choi. So let me first summarize our contributions. So we develop training-free data valuation score, which can be directly calculated from the data itself without training of a model. But at the same time, still, the score has meaning in the optimization and generalization of the neural network, but in the very simple structure. So we show that the developed score quantifies the effect of individual data instances in optimization and generalization of overparameterized, very wide, 2-layer, value-activated neural networks. So the developed score is based on the analysis of this kind of particular network, very simple version, compared to the many layers of network. But still, we see that the defined score is quite effective in experiments. And we show the applications of the score in data pruning in more complicated networks and also in noise filtering. And we show interesting relations between the defined score and learning difficulty of each individual instances by analyzing the training dynamics. So that's one-page summary of our contribution. So let me then move on to introduce our score. So our score is, as I said, based on the analysis of overparameterized 2-layer neural networks. And we use the previous setup and some of the theorem from the previous paper by Professor Aroa and others presented at ICML 19. So here, let me first briefly summarize the result of the previous work. So the network considered in the paper was the ReLU-activated 2-layer neural networks with M hidden neurons. And here is the output F of the model with the parameter W in the first layer, vector A in the second layer for the input X. And how it's defined is the following. So we take the inner product with the weight of the network and the input, and we imply the ReLU activation. And we just linearly combine the output of the ReLU activated the ReLU activation for the M hidden neurons with the weight AR. So here, network parameters are randomly initialized. So the vector, this D-dimensional vector, where D is the dimension of the input, is initialized as the normal distribution with mean 0 and the covariance kappa square identity, where kappa is the size of the random initialization. And AR, the parameter here, is uniformly sampled from -1 and 1. And here the data set is composed of n samples drawn IID from the underlying distribution D. And for simplicity, it is assumed that there are 2 classes, the binary classes, and all the input is normalized. So the image is vectorized and normalized for this analysis. And what we minimize here is the quadratic loss, the square loss between the output UI and the label YI, averaged over n samples. And it is assumed that the parameters of the second layer, the A, is fixed after the random initialization, and only the first layer's parameter WR are updated at every step K by using the gradient descent rule with the learning rate eta. Okay, so this is quite general setup for the overparameterized 2-layer ReLU-activated neural networks. And in the analysis and some theory, the important matrix appear repeatedly. So I just want to introduce the matrix first. So here, gram matrix H infinity, which is dimension n by n, associated with the ReLU activation is defined. And the ijth entry of this gram matrix is nothing but the expectation of the inner product between 2 samples, ith and jth sample, multiplied by the indicator random variable, which is equal to 1, only when the ReLU is activated both for the samples xi and xj, when w is the parameter for value. And what we take the expectation here is over w, randomly sampled from the Gaussian distribution.
So we can directly calculate this ij value by using the I sample and j sample inner product multiplied by the probability that ReLU is activated both per samples, defined by the angle between the two, the cosine, since xi and xj are both normalized vectors. And here we assume that this Gram matrix is positive definite, meaning that it's rank n and all the eigenvalues are positive. So that's assumption, and it can be actually achieved. This assumption is held for practical data sets with different samples in the data set. And the one-line summary of the previous work is the following theorem. So what was shown was following. So when we have enough number of neurons in the hidden layer and small enough learning rate, eta, and when we initialize the parameters of the first layer with very small size, kappa, then with high probability, during the training at the KAIST step, the amount of movement of the parameters from each random initialization measured by the Frobenius norm is bounded by this quantity, which only depends on the data. So here, y is the label vector, h infinity is the Gram matrix that was introduced in the previous slide. So this is only quantity depending on the data. And surprisingly, the amount of movement of neurons during training is bounded by this data-dependent data complexity measure. And the related result is following. The population loss is also bounded by the same quantity divided by n square root. Since for this kind of training, the training loss eventually goes to 0 if we have enough number of steps. The population loss is equal to the generalization loss. So this means that the network can be generalized if this quantity is small, generalized well. So let's look at what this quantity is actually about. So if we have the label vector y, which is aligned with the top eigenvectors of the Gram matrix, meaning the eigenvectors having larger eigenvalues, then we know that this quantity will be smaller, right? The reason is because of this inverse. So this matrix has the same eigenvectors as the original H infinity, but with the eigenvalues reciprocal of the previous one. So if your label vector is aligned well with the top eigenvectors, then this quantity is small, data complexity is small, so that means your network can generalize well, achieve smaller generalization error, and so on. So that was the previous result. So we know, at least for the two-layer overparameterized neural network, there is some data complexity measure that can describe the optimization and generalization of the neural networks. But our question was not about the complexity of the whole data set, but the complexity or value of the individual data set. So here is a very simple and natural extension idea to quantify the value of individual instances. So what we propose is the complexity gap score, which measures the complexity gap between the case when we use the full data set n samples and the case when we just extract the I sample point. So this is n-1 times n-1 dimensional matrix, n-1 dimensional vector, and so on. So CGI, the complexity gap score of the I sample, is defined as the gap between the data complexity when we remove the I sample point from the data set. So y minus I is the label vector except the I sample, and h minus I infinity is the Gram matrix except the ith row and column of the original Gram matrix. So we can, first of all, obtain two direct implications about the CG score. So what is the implication? So an instance with a large CG score is in some sense a difficult example, meaning that removing that from the data set actually decreases the generalization error bound much. So it means that in the data set, if you remove certain point with a large CG score, then the remaining data becomes much easier data set to fit by the neural network and generalize. So the CG score captures some difficulty of the example in terms of generalization first. And the second implication is that if an instance has a large CG score, then it actually is a sample that drives the optimization. Since the total movement of neurons are measured by this movement of the parameters from random initialization measured by the Frobenius network. And from the previous theorem, we showed that this quantity, the total movement of neurons, is related to the data complexity. And by removing some sample, if this data complexity is reduced much, then that means the optimization becomes much easier. You do not need to move farther from your random initialization. So a sample with large CG score is some sample that governs the optimization and also the generalization of the neural network. Yep, question?
Can I go back to 14? Yeah.
Yep, 14.
Yeah, this one.
Mm-hmm.
So according to the result, the generalization arrow bound is independent of M, eta, and kappa.
Right.
So, but in the main statement of the theorem, we say for sufficiently large M, sufficiently small eta, and sufficiently small kappa. So how small is small? Because intuitively speaking, if statement is dependent on some
right, yeah,
condition of M, eta, and K. So intuitively speaking, those
bound should depend on those parameters, right?
So, yeah.
Right. So I would say there is actually remaining terms here that I didn't show, and the remaining terms actually depends on those parameters. And what I say here is that if we have enough of such things, the remaining terms becomes the second order or negligible terms compared to the first order terms. So here in this slide, I just show you the first order terms.
It means it vanishes very fast.
Yeah, yeah.
So this technique is there any connection with PCA analysis also principal component? Because we are analyzing some data might be not very important compared to the risk. So
right. So when you look at this,
because you are using and value decomposition, so intuitively speaking, I think there's any connection with
right. Obviously has connection to PCA, but what's important here is the gram matrix here has no relation to PCA. So gram matrix actually captures the effect of ReLU activation from its definition. So this gram matrix actually captures the behavior of the neural network with the hidden layer activated by ReLU. So not just purely connected to PCA, but we encounter the effect of ReLU activation through the gram matrix in this quantity. Yeah. Any other questions from the audience? No. Then let me move on. So when you look at this, yes, this is data-centric score, but you might ask the question, isn't it complicated to calculate? It requires inversion of the matrix. And here we need to take the inversion for the original n-dimensional matrix and also the inversion for the n-1 dimensional matrix. And we actually need this inversion for every I, since we want to calculate the score for every samples. But good news is that actually you do not need to take inversion for this. You only need to take the inversion for this once, and you can calculate all the CGI for every I. So let me briefly explain the reason. So we will use the short complement, quite well-known method to actually efficiently calculate the inversion of the matrix when you remove certain row and column. So without loss of generality, we can assume that the data we want to calculate the score is located at the last row and column. Then what we want to calculate is the inversion of this n-1 dimensional upper left submatrix. And short complement actually show the relation between this inversion and the inversion of the original n-dimensional matrix. So by using this simple short complement equation, we can directly calculate the CG score only by using this H infinity inverse. We do not need to calculate H minus I infinity inverse. So this is good news in terms of calculation. And another point I want to address here is the geometric interpretation of the CG score. So we derived implications of the CG score based on previous theory about optimization and generalization of neural network, but we can add more additional interesting interpretation of the CG score by analyzing which sample would have higher CG score and so on. So for the analysis, for simplest, let's assume that there are n samples, but with balanced binary data set. So half of the samples belongs to the class 1, the rest half belongs to the class -1. And let's assume that a reasonable assumption, if the two samples belong to the same class, they have higher expected HI value P compared to the case when they belong to the different class. And why is that? Since HIJ is nothing but the inner product measures some correlation between I and J sample multiplied by this quantity, we can expect that if two samples belong to the same class, they will have higher correlation, higher inner product compared to any two samples from different classes. So this is quite a reasonable assumption, also can hold well with the real data set. And with this assumption, we can write down expectation of this gram matrix in a very simple form, a summation of the constant times identity plus some matrix that has the sub-block structure. So first of all, let me say that when I equals J, this is always equal to a half. Since the inner product is equal to 1, arc cosine is equal to 0. So if I is equal to J, HII infinity is equal to a half. So it means that we have diagonal fixed with a half, and off diagonal, either P or Q, depending on the two samples belong to the same class or not. So this has quite a nice structure. And if we assume that the first half of the samples belongs to class 1 and the rest half belongs to class 2, this has like block structure. So for this kind of structured matrix, we can exactly calculate the eigenvectors and eigenvalues. And one important thing I want to mention is that if P, the order of P is literal of 1/n, then this gram matrix is well approximated by the identity times some constant half. And using this kind of approximation, we can actually write down the CG score in terms of very simple information of the data. And let me explain what this means. So this is minus of this quantity, which is yi, the I is label, times y minus I transpose gi, when gi is the I column of the gram matrix. So even though it's complicated, it looks complicated, it's nothing but the difference between the summation of these HIJs over J over J having the same label as I and J having a different label from I. So it measures the gap between the average HIJ over the same class samples and different class samples when there are two classes. So we can expect that this quantity will be larger if some sample kind of represents the class. So if there is sample very typical in the class, it will have high correlation with the rest of the samples having the same label. And that means this quantity will be larger, much larger compared to that. So this quantity is larger, but due to minus sign, the CG score will be smaller. But imagine some sample that's kind of boundary between the two. So in cat and dog example, some object that looks like both cat and dog. Then the sample will be at some boundary between the two classes, the smaller gap between the two, and that will give you, due to minus sign, larger CGI. So it's kind of geometric interpretation we can directly obtain from this approximation. So regular or typical samples will have lower CGI, irregular samples will have higher CGI. Another interesting observation is the following. Let's just assume some image with the incorrect label. So effect of the incorrect label is nothing but the change of the order here. So your image is originally cat, but it is assigned to dog. So the order of summation is just change it, give you minus of this quantity, and due to minus sign plus of this quantity. So if the image has like incorrect label, for example, then the sample will have higher CG score naturally. So this kind of direct heuristic, but still meaningful geometric interpretation can be obtained from this approximation of the CG score. And we checked whether this kind of approximation actually holds with the data by generating two Gaussian synthetic data sets. So from the two Gaussian samples, two Gaussian distribution, we sampled 1,000 samples from each of the Gaussian. And here the class is there are two classes, and the class 1 has +1 and class 2 has -1 in this first dimension. That's the only difference in the mean. And we plotted the first dimension versus CG score for these 1,000 samples of class 1 here and class 2 here. So first of all, you can observe that the samples near the boundary indeed have a high CG score. And as we know, the samples near the boundary are the important samples in training the classifier to set the correct boundary between the two. So it shows that CG score actually can capture some important data in terms of training classifier. And we also check this fact. So we artificially randomly flipped 10% of the data and check whether such data with label noise indeed has higher CG score. And here, the purple and green ones are the samples with incorrect labels. And we could see that, yes, CG score is higher for such label noise data. But this is synthetic experiment. Someone can ask whether this kind of trend also holds for real data set. So let me show you the real data set example here. First, MNIST. So we just, since CG score is data-centric score without training, we can just calculate the score from the data itself. So this is the result. So MNIST is composed of 10 classes of handwritten images from 0 to 9. And here the 3 rows shows the lowest scoring examples of each class. The upper rows shows the high scoring examples. So for example, class 0 or class 1 and class 2, you can see that these low scoring examples are really typical ones, looks very similar to each other. But high scoring examples look a little bit atypical, let me say. And we checked this red rectangle for the images that might be misclassified. So here, for example, the class 4, this image should be a class 7, but has the label 4. And we could detect such images by just looking at the CG score. So this is the top 3 high scoring, top 3 low scoring examples. More complicated data sets, if I can, we could also check the trend. So due to the space, we just show 2 classes, the cat and dog. So low scoring examples look quite cat and dog, but high scoring examples, it's quite hard to say this is cat or this is dog and so on. So with this kind of CG score, that can be directly calculated from the data and label. Yes, we could detect some hidden information of the data in terms of irregularity, either due to the irregularity of the image itself or due to incorrect labels. So then let me show you some applications of our score, how it works in real applications, including the data pruning, noise filtering, and related to the training dynamics. So first, data pruning application, I explained how this kind of experiment worked. So here, x-axis is the portion of trained data set we used after the pruning. Y-axis is the test accuracy, the generalization performance. And the first row shows the case when we prune the low value data first, low scoring examples first. And the second row shows when the case when we prune the high value data first. So for this first row, this red is the random case when you randomly remove certain portion. And our score is the blue one here with the standard deviation shaded region compared to 2 other scores, which require the training of a neural network, but these 2 scores are kind of SOTA scores in data valuation, so we wanted to compare. So we can see that our curve actually achieves good performance, quite competitive, even without training of a model, just direct calculation from the data. And this experiment was done in not 2-layer neural network, but ResNet 18 and ResNet 50 for Cypher 100. So even for more depth, complicated network, our score actually works in terms of data valuation. And this second row, since we prune the high value data first, if we have the curve dropping rapidly, that's the good one. And we can see that our curve, the blue one, achieves one of the best results. And that means high scoring examples are indeed essential examples you don't need, you must not remove in terms of achieving good generalization performance. So that was first check. And second application, noise filtering. So I said that our score is effective in detecting noise. So to see the effectiveness here we artificially corrupted 20% of the data in FMNIST and CIPHER 100. And we first check whether, here is the density for clean and noise level. So we first check whether indeed the noise samples has higher CG score. So yes, it indeed have the higher CG score, but a little bit interesting, one more observation is that for simpler data set like FMNIST, this clean and red one can be actually quite perfectly divided in terms of the CG score. But more complicated data like CIPHER 100, there is quite overlap between the clean and noise CG score densities. And that means even without label noise, some of the images are still very complicated in terms of the data complexity. So there can be some overlap when you just look at the CG score. So we check the detectability of noise labels by using our score, by examining some fraction of data sorted by the CG score. And for FMNIST, we could see that when we examine 20%, almost all the noise labels could be detected. But the performance is a little bit lower for complicated data sets, CIPHER 100. So our score is not perfect score for filtering noise, but it's effective in simple data set. That was the message we got. The last application is training dynamics. So training dynamics to see, so training dynamics basically kind of see the examples that are hard to learn during training or easy examples during training. So we could observe some correlation between the difficulty in terms of training dynamics with our scores by generating 10 subgroups ordered by our CG score. So this blue one is the easiest group from our perspective, the CG score, and red ones are the hard ones, high CG scoring group. And we check as the training goes on, how the mean of the loss and accuracy changes for such easiest group and hardest group. And in terms of training dynamic itself, we could also show that the high scoring groups, the mean of the loss converts slowly, and the accuracy also converts slowly. And there is another experiment here. We calculate the neural tangent kernel velocity, how the neural tangent evolves for subset of the data. So this can measure or this can detect some subset of samples which really drive the optimization. So we could see that the high scoring groups are actually the samples the neural network tried to fit or struggled to fit. So with this kind of experiment, yes, we could see the correlation between the CG score and the difficulty in terms of training. So summary for the first part, we proposed the CG score, a data-centric valuation score based on the analysis of the overparameterized two-layer neural networks. And we showed the geometric interpretation of the CG score, and we could also efficiently calculate the score by using the nice short complement type of calculation. And what we showed was that such samples with high CG scores are somewhat irregular samples, either due to image itself or the label noise. And by using such intuition, we could design data pruning, noise filtering, or training dynamics analysis kind of experiment to show the effectiveness of our score. So some of the future directions, first of all, our score is based on the theory of the two-layer neural networks. Of course, we would like to get more support justification of the proposed score in terms of theory by analyzing or generalizing theory for network with more depths. So that would be interesting direction. Second direction, our score is really data-centric score. It really can be calculated by using data vector and the label itself. But we might be able to improve the score by modifying the definition in terms of the feature if you have any pre-trained neural networks. So in terms of feature, how can you improve this kind of score? Still computationally efficient, but more effective, possibly, is another interesting future direction. So this is the first part, and now I want to move to the part 2, data valuation without labels. But before that, if you have any questions, please let me know. Yep.
One question. So all theories are derived from binary data sets. I wonder how do you do experiments for the evidence part?
Right. So there are 10 classes. So we actually calculate the score with respect to each class. So class 1 versus other classes. So we randomly sample the number of samples from all the other classes, 2 to 9. And then we measure the score within the class 1, get the order, and we do it 10 times, basically.
Basically, a computation combination.
Right. And for sidecar 100, since there are 100 classes, the computation is quite hard. So we kind of self-sample the data set from each class to reduce the complexity, since the inversion takes n to the 3 kind of standard complexity. So we reduce the size and then do the average kind of Monte Carlo calculation.
Because I see that loss that used is just a square loss, right? That works for primary. Wonder that with multiple tables. Is there a better way to calculate the loss?
Yeah, possibly with theory using such cross entropy laws or other kind of laws. But currently, yes, since our analysis, the based analysis is based on the quadratic laws, we do the binary thing, just number of times equal to the class of the data set. Yeah, great question. Any other questions? Okay, then let me move on to the data valuation without labels. This is the published work at last year's NeurIPS with the title Self-Diagnosing and Diagnosing Underrepresented Samples in Generative Adversarial Neural Networks, joint work with 3 of my students, Jinny Lee, Harry Kim, and Young-Gyu Hong. So most of the previous score actually used the label information. But as I said, there are so many other data sets without labels. So the question, natural question we had was, how can you quantify the value of each instance without labels? So let me first summarize our contributions. So in this part, we just focus on one particular network type for generative model, again, not the VAE or so on. So we focus on GAN, generative adversarial network, and we identify the hard-to-learn samples by analyzing, defining score, effective score that can be computed during the training of GANs. So our score for this case based on the training dynamics of GANs. And while the intuition was there, in GAN training, samples that are hard to learn, difficult samples, are some minor samples or irregular samples, samples from some sparse region of the data manifold of the training samples. And since those samples hard to learn are actually irregular samples or hard to learn samples or minor samples, those samples are actually valuable samples in training unsupervised learning, the GAN network. So we kind of detect those samples by defining new score, and then we emphasize those scores by exposing those scores more frequently in the training of the GAN. So that was the high-level idea. So let me go to the definition of the GAN laws first. So again, the goal of the GAN is following. Given only data instances without labels, what we want to do is to learn a model or generate a model that can generate fake samples that look just similar to the real samples. So human beings cannot actually distinguish the fake samples generated from GAN from the real samples when the GAN is trained well. But GAN does not actually give you the distribution of those samples. It just generates the samples. And GAN was proposed by Goodfellow in 2014, and this is one of the widely used generative model due to its high quality of the fake samples. And it's basically the two-player game between discriminator network and the generator network, D and G, optimizing this kind of min-max loss. So what's going on is following. In the generator network, we put the random noise and we aim to generate fake samples. And the discriminator tries to distinguish fake samples from real samples. And through that process, the discriminator gives some feedback to the generator for it to generate more realistic samples. So this is the min-max game. So discriminator tries to maximize this loss by identifying real samples. So for real samples, the discriminator should output 1, and for fake samples, G is the fake sample with the input G to the generator. So for fake samples, you need to reproduce like value 0, so classifier, fake or real, to maximize this cost. while the generator tried to minimize this cost to make this discriminator output also equal to 1, right? By generating the realistic fake samples. So that's how the GAN works. Well-known properties of GANs. GANs are very good at generating high-quality samples, but it's well known that they often fail to learn sparse region of the data manifold, meaning that in your data set, the major samples, like for cell-based data set, the majority is the white women. And when you train again with such cell-based data set, the generated samples are mostly white women. But minor samples like Asian or black hair people or people with eyeglasses, they are rarely generated in GAN when you do not focus on such diversity issue of the sample generation. And also, it suffers from mode collapse. GANs are very good at generating realistic samples, but they generate very similar type of samples, not the diverse one. So certain mode is eliminated, even it exists in the training data set. So it means that during GAN training, GAN sometimes ignores some minority of the data set. So there exists underrepresented samples. So our goal is to improve diversity in sample generation while not degrading the overall quality by using the data valuation, by detecting and emphasizing some underrepresented but valuable samples. So here is the overview of our strategy. 3 steps. So this is how we trained again. Blue one is the fake samples. Yellow one is the real samples that into the discriminator, and discriminator gives the feedback to the generator. And in the process of training, by analyzing the training dynamics, or more in particular, the output of the discriminator, we will detect some underrepresented samples in these training instances. And then we will emphasize those samples in the phase 2 of the training by showing the sample more frequently in this network. So 2 challenges, a very simple strategy, but still 2 challenges: how to detect underrepresented samples and how to emphasize. So this is about scoring scheme, and this is about designing algorithm. So challenges, of course, if we can calculate log density ratio between the data distribution and the generator distribution. Yes, we can easily detect which one is overrepresented, which one is underrepresented. So if we have this LDR that can be calculated for every training instance X, if this value is positive, that means P data X is larger than PGX, meaning the data is underrepresented. So PGX is the generator distribution, P data X is the data distribution. So if this is positive, P data is too much at X compared to the PGX, so data is underrepresented, so we need to emphasize such samples. Opposite case, if this is negative, PGX is larger than P data X, meaning the generator generates too much of such samples, so we need to kind of suppress the frequency. This data is overrepresented. So LDR is a good quantity to see the gap between the P data and PG at certain training instance X. But the, of course, problem is we do not know that. We do not know data distribution. That's why we trained again. And we do not know PG either. This is not autoencoder type of generator model. Again, just generate the data, but PG is kind of implicit, hidden in the network. So here is the idea how we approximate that log density ratio. So we will approximate it by using the discriminator output. The reason is that, so GAN solves this min-max optimization. And given generator, given PG, if you solve this maximization, the D star X that maximizes this loss is nothing but P data over P data plus PG. And when you plug in D star X here, this is exactly what you want to get, log density ratio. So that's the simple but effective idea. But there are many problems here. First of all, discriminator during training is not equal to D star X. Discriminator is not perfect due to the instability in the training of the GAN, and also since we want to do something before the discriminator generator converges to some point. So in the training, if some sample is underrepresented, we want to do something, not at the last, but in the middle or beginning. So this kind of approximation is not working in reality. So here we show that during the training, when you check the LDR estimated by the discriminator output for 3 different random samples, it's really like fluctuating. We cannot extract information from this LDR estimate. So then how can you solve this? The idea is to use some statistics over the training, and just 2 simple statistics we can use: mean and variance of the LDRs. So LDR-n, LDR mean, is defined as the average of this LDR over T steps during training. And we will also look at the variance, LDR-b, not only the mean, measured over these T steps. And let me then explain what these 2 scores can do. The role of these 2 scores are a little bit different, so let me explain that. So we first empirically show that LDR-n, the LDR mean, is quite effective in detecting underrepresented samples. So to check that, we designed simple synthetic experiments using 25 mixture of Gaussians with 25 modes here representing. So here for 25 modes across epochs, we measure the LDR-n for each mode, averaged over the samples belonging to each mode. And we actually see the correlation between this LDR-n and the generated samples, the missing mode. So for example, this mode has index 5, and this mode is not appearing in the generated sample, missing mode collapse. And we could see that for such mode, the LDR-n calculated at the training samples are indeed higher. The red one is high here. And once it starts appearing in the generated sample, the LDR-n becomes the lower. So just by measuring the LDR-n on training samples, we know whether the mode is generated by the generator or not. And we could also see the LDR-n and the number of quality generated samples, the correlation between the 2. So if certain mode has high LDR-n, that mode samples is not generated in the generated samples. It's missing, mode collapse appears. So from this experiment, empirically, we could observe that LDR-n is effective in detecting missing modes. Next, then, what is the role of the variance LDR-b? So we claim that LDR-b is effective in detecting minor features. So again, this is unlabeled data. We do not know which sample has any minor attribute or not, but we claim that LDR-b is effective in detecting minor features, samples with minor features. So first of all, we first checked the quality of the generator on minor samples. So we trained the generator, or we trained again when the training data has very unbalanced attribute samples. So here, major 90%, minor 10%. For this first example, the major is the red attribute, minor is the green attribute. For the second example, we just mixed 90% of the MNIST, 10% of the FMNIST. And we could see that the quality of generated samples for minor features is much worse compared to the major samples. So this MNIST is quite good in terms of the quality of generated sample, but FMNIST, you cannot actually see what is this one, and so on. So again, it's struggling with generating high quality minor samples. And we just calculated the LDR-b for the training samples of major group versus minor group. And we could see that, yes, LDR-b is higher for minor groups, both for colored MNIST example and MNIST-FMNIST example. So empirically, we first check our intuition works. So again, it's effective in detecting minor features. And we also did some theoretical analysis showing that LDR-b can capture the minor samples, minor features. So for that, we considered simple logistic regression model for the discriminator. So when xi is the image, fxi is the feature of that input, and the discriminator under the logistic regression model take the inner product with the theta to the feature and generate this output, which is the reality score, the probability that it's real, 1 + 1, given the input vi and the parameter theta. And from the Bayesian perspective, we analyzed this discriminator. So assuming the prior distribution of theta with sample from prior distribution of theta with the normal distribution with mean 0 and variance S0I with some hyperparameter S0, we can calculate the posterior distribution with this prior distribution and the conditional distribution that can be calculated in terms of this formula as the parameter theta. And now we do the Gaussian approximation for this posterior distribution by finding the theta that maximizes the log likelihood, and by finding the covariance matrix, which is nothing but the minus of the second derivative of the log density. So this Sn minus Sn inverse, which is the inverse of the covariance over here, can be written in terms of the summation of d times 1 minus d and vi transpose, when vi is the feature vector of the ith sample. And now what we've done was approximate the LDRV, the variance of this quantity, by the Taylor extension at the parameter theta equal to the theta MAP, the optimal point. And we could show that LDRV is related to the VI transpose SN VI, when again, SN is the covariance matrix defined in terms of the summation of D or minus D and VI transpose. So quantity here, so Sn, let's assume it's also full length. So eigenvectors of Sn are actually dominated by the major direction of the features. So if your sample has some minor feature, minor direction, then it will be not aligned with the top eigenvectors. And due to inverse here, that will give you higher LDRV. So that's the intuition we could get from this analysis and approximation. So binary feature vector, which has a small component on the eigenspace formed by the majority of VI, tends to have a higher LDRV. And that's why with LDRV, we can detect samples with minor features, even without any labels. So the score we defined is just a combination of LDRN and square root of the LDRV with certain hyperparameter K. And we call this discrepancy score. And we first check whether the discrepancy score actually can detect samples underrepresented. So for the experiment, we trained the generator and generated samples, and then we collected, so we examined the training samples with the discrepancy score, and then collected the images with the lowest discrepancy score and images with the highest discrepancy score. And we could actually see from the figures itself that images with lowest discrepancy scores are actually the major samples, the white women, which looks quite similar to the generated samples. But images with highest discrepancy score are very different from the generated samples. And that means, so all these data are in the training data set, but when you train again without any care, again, just focus on the typical samples with the low discrepancy score. And we here compare the pixel count histogram of the three groups, the lowest discrepancy score group blue and the highest discrepancy score red and the generated sample green. So in this histogram itself, you can see that the blue and green are similar, but the red is very different. So samples with highest discrepancy score actually has very different attributes that is not yet reflected in the generated samples. So they are indeed underrepresented. So by checking that fact, now we designed algorithm to emphasize underrepresented samples. So our algorithm is composed of 3 phases. At the first phase, we trained again for certain steps to actually calculate the discrepancy score based on the statistics of the discriminator output. And at the second phase, we designed a score-based weighted sampling, which is the weighted sampling method that just show the underrepresented sample more frequently during the training of the GAN. So we just expose underrepresented samples more frequently to emphasize those samples. But that kind of weighted sampling always gives bias in terms of the distribution you're aiming to learn. So at the last phase, we kind of correct such bias by just simple rejection sampling. So we generate the sample, and using the rejection sampling method, we just reject some of the samples to match the distribution between the data distribution and the generated distribution. So this is kind of fine-tuning step, let me say. So we checked the quality of our methodology, the DIA-GAN, self-diagnosing GAN, compared to other previous methods for improving diversity and quality of the GANs in 2 different GAN structures on 2 different public data sets with respect to 4 different performance scores. So FID is some distance measure between P data and PG. Inception score measures the quality of generated samples. Precision measures the portion of your generated samples inside the data manifold. So how precise your generated samples are. Recall measures the fraction of generated samples. Fraction of training samples in the manifold of generated samples. So how much of the generated samples are recovered in the, how much of the training samples are recovered in the generated samples. So FID, smaller good, distance gap, inception score, larger good, precision, larger good, recall, larger good. And our DIA-GAN method, yes, actually could achieve good performances with respect to this FID inception score, and it achieves good recall rate, but with slight drop of the precision. So there is still some trade-off. And another interesting experiment, since we claim that our score can detect minor samples, we actually checked whether the generation of minority improves in GAN. And for that, we consider the Celebi dataset, which has diverse minor attributes. So in Celebi dataset, like the data has only 2% of bald people, 4% of double chin, 6% of eyeglasses, and so on. And these minority samples are even, the minority level is deteriorated when you train again without any care. So even though the eyeglasses should take 6%, when you use the vanilla GAN, it takes only 3%. So minority are not well generated in vanilla GAN. And now we checked the scoring thing, whether our score can detect such a minority group. So we could check that with such minor attributes, the scores are higher compared to the images without the attributes, both in terms of LDLV and this score. And we show that the recall rate for such minor groups are increased, and the accuracy rate is also increased. So for the eyeglasses, without care, only 3% of the images, generated images, have the glasses. But with our method, emphasizing minority, it is increased to 4. And for all the considered minor attributes, yes, we could see such trend. So our GAN is actually working in the way of emphasizing minority, increasing the portion. Some interesting last figure I want to show. Oh, sorry, I'm a little bit out of time. Last figure. So comparison of generated samples. So our DIA-GAN is working in phase 2 after you train the GAN for a while. So we just compare the vanilla GAN and the DIA-GAN. DIA-GAN is our method with emphasizing. When the generator is fed with the same input, but vanilla GAN stops at a certain point and DIA-GAN use the emphasizing step. So with the same input to the generator, the generated images are still quite similar, but surprisingly, certain minor attributes suddenly appear with our method. So no eyeglasses had just came out with our method and so on. So minor attributes start to appear with our method for similar images. So that was quite interesting and surprising observation. So summary for this second part, we provided 2 measures to detect underrepresented samples during training of the GAN. So our original goal was to define some score for data valuation without labels. So we just focused on GAN training, and we could define the score based on actually discriminator output, GAN output, to detect underrepresented and also important or minor samples. So LDLM and LDRV, and we defined the discrepancy score based on these 2 scores, detecting missing mode and detecting minor features. And we designed the algorithm to emphasize those minor things to increase the diversity in sample generation. Interesting future direction. So there are many works going on for fair machine learning or fair deep learning. So such fairness is in terms of emphasizing minority in sample generation, or or have fair classifier and so on. And we believe that our method, our idea, especially the scoring mechanism, can be used in designing fair generative models. Because when you have no like labels for the data set, you do not know what kind of attribute exists, what kind of attribute has some unbalancedness to define the minority. But we show that with our score, we can quite naturally detect such minor attributes and minor samples. So after the detection, designing algorithm is a little bit different story, but there can be many different types of algorithms you can develop to emphasize those minor samples. So I believe that this kind of future direction would be very interesting and promising. So concluding remarks of this talk, we consider the data valuation, but computationally efficient and also effective at the same time in the setting without training of a model for computational efficiency and also without label information. And for these two cases, practical cases, we believe we could develop nice scores to compute and which are effective in terms of many applications, data pruning, and fair generative models and noise filtering and so on. And some fundamental questions that I still have. So first of all, for the labeled case, we show that our score is effective in both aspects of noise filtering and also in identifying important irregular samples. And the trend was that when you have some noisy labels, the highest scoring images are actually noisy labels, and the second highest groups are clean label but irregular samples. But there is no really strict threshold in between the two groups. And when you consider like robust learning, robust to any like label noise, but still want to achieve good quality, good generalization quality, you need to have some automated way to distinguish the noise label data versus irregular but quite important value of data. So that kind of direction is very, for me, very interesting and important direction, I think, to achieve both the robustness and also the good generalization capability. And the next fundamental question I have is the following. So if you read many like deep learning papers, many of the papers actually use diverse data augmentation method, like mix up or translate your image to generate another similar image and so on, in contrastive learning and so on. So data augmentation tries to basically increase the volume of the training data to have better generalization. But on the other hand, data pruning do the opposite. They just remove the data for efficient training. So the philosophy there is somewhat contradictory, right? Data pruning just want to find good quality data with removing the redundant one. Data augmentation just add the data, possibly useless, but sometimes useful without that much care. So these two contradicting things are going on separately, but conflicting philosophy. So I would be interested in understanding so more theoretical analysis of these two things, what's really going on there, and also practical algorithms to find good quality data and also effective mix-up or data augmentation method only on the subset of the data and so on. So this is the question that I have, and I would be happy to discuss or possibly work with you. Okay, thank you for your attention for a long time.
Any questions? So for the second part, right, where you pick the linear combination of
this frequency score
and the mean part and the variance part of standard deviation part, and you achieve better scores later on in terms of recall and prediction and so on. Do you have to tune the value of K?
Yes, so we actually tuned the hyperparameter, and we actually in the paper showed also the robustness. So K should actually depend on the characteristic of the data set. So for some data set, LDRV is much more important, like cell-based data set, if there are many minorities and so on, K should be increased. And for a simpler data set, maybe LDLM is just effective, detecting missing modes. And K should depend on the data set, but we also could show somewhat robustness. The performance is not that much changing, but there exists optimal K hyperparameter. Thank you for the question.
I actually do not know background of much of you guys. So I actually had background in information theory, more mathematical things like proving theory and so on. And this is kind of new stream for me, using some intuition from data science and information theory to define good score and a little bit of analysis, kind of heuristic, not the theorist, and proving the empirical performance gain and so on. So, but I'm interested in both of that. And another stream of my work is about like crowdsourcing data acquisition and probably good performing algorithm design and so on. So I would be also happy to discuss about the other topic as well if you have any questions. But for this talk, if you have any question, I would be happy to answer as well. Yeah.
You consider the data valuation?
Have you considered data valuation without training and without data information?
Good question. Right. We haven't yet. Yeah. So, right. That's kind of also interesting, and there are also some classical works, of course, going on for the density estimation. And in density estimation, you can actually, by using the density estimation, you can actually define scores, whether the sample is from some sparse region of the data manifold or it's very typical sample and so on. And that kind of score would be also used in terms of training. But I'm not sure whether that kind of score would work for different types of generative models, because again, they perform very differently. So yes, for this case, yes, we just focused on GAN training and used the training dynamics. Yeah, thank you for the question.
Hello.
Hello.
In data training, should we keep all the data with high simple score, or should we balance it some way? I was focusing.
Oh, right. Yeah, so there are some results. We actually, when we deal with like 40%, 30%, that's quite a large portion still, right? So for such kind of range, we should keep the high scoring things. But when you actually sample really small number, then the story becomes a little bit different. So since high scoring samples are really irregular ones, not typical ones, but if you sample, for example, per class, like only 10 samples, 50 samples, when the number of examples of the class is like 5,000, then maybe high scoring examples will not be a good choice since they do not represent the class, right? So there should be some balance, right? And that's another stream, not the data selection or pruning, but there is work named data distillation and data condensation. And in the field, they actually generate the data that represent the class, but the number is quite small, only 1 data per class, 10 data per class. And in that kind of region, you need to consider typicality as well. Yeah.
Does anyone else have any questions?
All right, if not, let's thank Taiwan.
Thank you very much.